In this section, we're going to discuss separation of variables to solve differential equations. So if we notice from this expression here, in real general terms, if we have a differential equation here that is of this form, in other words, we have a term here that's a function of x, and a term here that's a function of y multiplied by the derivative or that differential expression, we can effectively separate the variables. And separation of variables, all that means is making sure all of the variables are of the same type are on one side, and then all the variables of another type are on the other side. So in respect to these type of functions, we're just going to make sure that our x's are on one side and our y's are on the other. So for this sort of generic setup, we could subtract the variable in terms of x from both sides and end up with the function in terms of y times the differential expression equals opposites the function in terms of x. And then we could separate the differential expression. And separating the differential expression in effect is just, you can think of it as multiplying both sides by dx. It's kind of a way to gloss over what's happening here, but really this differential expression is very similar to working with a fraction. So as we relocate that differential expression to that side, then we have a function in terms of y with its differential expression, and another function in terms of x with its differential. And so we've separated the variables, with the y variables being on one side and the x variables being on another side. So if we look at an example here, we have a differential equation, and we have a differential expression here. It's just noted differently. So the first thing I would do is rewrite this with its differential expression written as a ratio. And then we can go ahead and we'll bring the everything that's a function of x over to the right-hand side here. So we'll subtract root x from both sides. We'll have square root of y dy dx equals opposite the square root of x. And then we can bring the differential expression dx to the other side by separating it from that differential expression dy dx. So we have something that looks like that. And then we can go ahead and integrate both sides. So we've separated the variables. The y's are on the left, the x's are on the right. And we're going to go ahead then and, there we go. We're going to go ahead then and integrate both sides. So integrating the square root of y is, we can think of that as integrating y to the 1/2 power. And so integrating y to the 1/2 power is bumping this up by 1, that's 3/2. So taking that reciprocal, 2/3 y to the 3/2. And then really we have a plus c. I'm going to put a plus a c1 here just to make a point, but I won't do that from this point forward then. And then integrating this, we have opposite 2/3 x to the 3/2. And again, I'll put a constant of integration here as well, because we did technically anti-differentiate both sides, so each side leads to a constant. You don't really have to do that, because if we take this constant over to the other side, excuse me, that's the wrong subscript. If we take this constant over to the other side so that we just have a constant on one side, then a constant minus a constant is just another constant. So I generically put a constant c on the side of the expression that has the variable x. And like I said, this is the last time I'll actually do the subscript c1 and c2. I'll just throw a constant on the right-hand side from this point forward. But that's the reason why you can do that, is because when you take a constant over to the other side anyway, it just turns into another constant. So simplifying this, we've got something that looks like that. And so at this point, we can solve for that constant of integration. And so the initial condition was at x equals 1, the function y in terms of x is 4. So I can go ahead then and plug that into the expression. So we have 4 to the 3/2 power equals minus 2/3, 1 to the 3/2 power plus c, and then we can go ahead and solve for c. So 4 to the 3/2 power is something you should be able to do in your head. What I do is I do the denominator first. 4 to the 1/2 power, that's a square root. So square root of 4 is 2. 2 cubed is 8. So we really have 2/3 times 8. And this is equal to minus 2/3 plus c. And so solving this, we get 16/3 equals minus 2/3 plus c. So we have a c of equal to 18/3 after we bring this over as a positive 2/3, which is equal to 6. So we have then the function, it looks like 2/3, if we go back to this step here, 2/3 y to the 3/2 equals negative 2/3 x to the 3/2 plus 6 is that function. And if we take a look at that in terms of graphing it, we can kind of take a look at that, and that looks like this. So if we solve this expression for y, we end up with something that looks like this, and we see that this function kind of looks like this, hits off that point, and then comes back up like this. And so that point x equals 1, 4, we're talking about right here on that function. And in looking at the slope field, you should be able to come up with the differential expression. That's a Calc AB skill. So we're talking about coming up with an expression of dy dx equals. And so if we look at these slopes, everything along the y-axis has a slope of 0. So if that's the case, for any y value, you need to have a slope of 0. And 0 happens to be the coordinate for the x coordinate along this axis, right? This is 0, this is 0, 4, this is 0, 3. So if we need a slope of 0, then in the differential expression, we must have x in the numerator, because that's the value of x at all those locations, which is happens to be the value of the slope as well. If we look along the horizontal axis, we can see that these have infinite slope, and these coordinates are minus 4, 0, and minus 3, 0, and so on and so forth. So if this has infinite slope and its y value is always 0, then the way we can get infinite slope is to make sure that the y coordinate is in the denominator. And then we have to kind of look at what's happening in these quadrants. This is the first quadrant, and in the first quadrant we have a positive x and a positive y, but we have a negative slope. So if this is an expression for the value of that slope field, we're going to need to have an opposite sign in that expression, because we want a negative slope in the first quadrant, and these coordinates in the first quadrant are positive. So there's the expression for our slope field. It's a quick review of an AB concept that you probably are familiar with. And so here's that differential expression. We can draw some general, we can kind of sketch some general solutions here. So if we look at this, you see how it does look circular. So I'm just going to kind of, as best as I can, kind of draw my series of dots around the 4 quadrants here. So there's a possible solution. Here's another possible solution. So what we have is we have this solution that happens to be a family of circles that are concentric about the origin. And if you remember back to geometry, we can get those equations. We know how to write equations for circles that have a certain xy coordinate for the center. And I'll come back to that at the end of this problem. But for now, to get these, to get the general solution here, we can just go ahead and separate this differential expression and come up with the general solution using calculus. So we're going to go ahead and multiply both sides by y. And so we end up with a y dy over dx equals opposite of x. And then we're going to go ahead and separate that differential expression by taking the differential dx to the other side. And we'll go ahead and integrate. And so when we integrate this, integrating y gets us 1/2 y squared. Integrating opposite x gets us minus 1/2 x squared. And I mentioned earlier that I was just going to throw the c on the side of the x coordinate, or the x variable. I'm not going to do a c1, c2 thing anymore. So here is our general solution. Now I'm going to rearrange this. I'm going to take this to the other side. So if I take that expression 1/2 x squared to the other side, I'm going to add its opposite. And so I have 1/2 x squared plus 1/2 y squared equals the constant of integration. And so if we look at this, we can start to see the form of a circle here, right? We've got an x squared plus a y squared. We've got nothing in parentheses, which gives us our center of 0, 0. And so, and we have the same coefficient out here, which means we don't have any eccentricity. We don't have an oval or an ellipse, more specifically. So I'm going to multiply through by 2 just to clear the fractions. Not a big fan of fractions, which gives me 2c out here. And so there's my general solution. So if you remember back to geometry, and we look at maybe this circle here that goes through, we look at the circle here that goes through the axes at 1, we would say that specific, that particular solution here, that particular solution is x squared plus y squared equals radius squared, which is 1 squared, or x squared plus y squared equals 1. So there's a particular solution to this family, in other words, a particular solution to this general solution. So in that case, you know, c would be 1/2. And so, so we can see that we really just have a geometry application here in terms of coming up with the a particular equation. So we could have actually started from this geometric application and then just backed up and said, well, the 1 really has to be a constant of integration because it is a constant. Approximate a particular solution to a differential expression. And so by now, I think you're beginning to see the interrelationship between separable differential equations, slope fields, and Euler's methods. They're all kind of complementing one another when it comes to finding solutions. So in the last example, you saw a slope field. You know, we started with a slope field and generated a differential expression. This first example, we started with a differential expression. We could have created a slope field. And for each one of these problems, we could have created a table and done Euler's method to get an approximation without using calculus. And so that's what we're going to do here. We're going to go ahead and generate a table so that we can approximate this without using calculus. And so when we do that, we have to use the slope-intercept form of the expression for a line, because with Euler's method, that's the whole idea, is to create these small segments across our delta x, in this case our point 2, so that we can approximate a value out into that next section. And so our differential expression we have here dy dx equals 6xy squared. And so if we kind of solve that, we have dy dx equals the opposite of 6xy squared. And so this is really minus 6xy squared. That's what you're using to calculate this. So we're going to start at 0, and our initial situation, or our initial conditions are 0, 3. So we're going to start up here at 0, 3. And we're going to go ahead and calculate the value out here at 0.2. So we have our differential expression, and so that's going to calculate our slope here. So our slope is 0. And so as we step out 0.2 with a slope of 0, so think about starting here at 3, our slope of 0 is a horizontal line. If we step out at 2, we should be still there. And we can check that. Here's our expression for our line. And you should recognize that as, and I'll write it in the order we see it here. This is b, the intercept, y sub 0, and then plus, and y prime is our slope, and delta x would be our x. So this is what I'm talking about, the slope-intercept form of a line. So we're going to plug in initial value of 3, slope of 0, step of 0.2 gets us 3. So there's our new point. So for this function, the first approximation across 0.2 is just this horizontal line. So now we're going to take this point, 0.2 comma 3, and we're going to go ahead and calculate what the new slope is going to be for this section of the graph. So we have minus 6 times the x value, which is 0.2, times the y value, which is 3 squared. And when we crank all that out, we get .1, no we don't, we get 10.8, I believe. Let's just get a calculator out here real quick to verify that. There we go. Okay, so we have -6 times 0.2 times 9. 3 squared is 9. So yeah, negative 10.8. So we have negative 10.8 is our slope. And so our step here is we are at 0.2. We're going to add 0.2. So our new x is 0.4. So we're out here at 0.4. And our new y is going to be y sub 1, which is 3, plus our slope, negative 10.8, times our step of 0.2. And when we do 3 times 10.8 times 2, we get, so we have 3 plus 10.8 negative times 0.2, we have 0.84. So 0.84. So we have a slope, if you think about this, we have a slope of negative 10. That's a pretty big slope. So across 0.2, we're going to fall a lot. We're going to fall all the way down to 0.84, so just under 1. So here is that second approximation, okay, for Euler's method. And then, so that becomes our new starting point. We have our 0.4 and 0.84. And we're going to go ahead and calculate our slope. So it's minus 6 times 0.4 times 0.84 squared. And that value is negative 1.693 for a slope, so a much smaller slope, but still negative. If we take our step, we started at 0.4, we're going to add 0.2, so we're going to be at 0.6. And if we calculate our new y, our old y is 0.84. Our slope is negative 1.693, and our step is 0.2. So when we calculate all of this together, we have 0.501. So with a slope of 1.693, it's still negative, so we're still going down a little bit. So we've gone from 0.84 there to about 0.501. Okay, so it's approximately like that. And then we can continue this process here. We're at 0.6, and we're at 0.501. And so we can calculate our new slope again. So negative 6 times 0.6 times 0.501 squared. And when we calculate that, we get negative. Notice that's still negative because we've got this negative sign out here. We're going to have always a negative slope for this example, 0.903. And our new x after we apply our step is 0.6 plus 0.2 equals 0.8. And our new value for y is going to be our old value. We start out at 0.501. We add to it our slope times our step. So we're going to have negative 0.903 times 0.2. And when we calculate all of that out, we have 0.32. So it's kind of flattening out as we notice our slope is getting negative but closer to 0. So we would expect that this starts to kind of flatten out. So we might be looking at something that's pretty asymptotic with the x-axis. I'm just going to speculate on that. And then we're going to repeat the process. We're at 0.8. We need to go to 1. That's what the final position tells us. So we need to do this yet another time. And doing this 4 or 5 times in a free response question is reasonable. I've seen that on AP tests in the past. So calculating the slope here, negative 6 times 0.8 times 0.32 squared. And that gets us negative 0.49. So still flatter. So our new x is going to be at 1, which is where we need to end. And so we got to calculate our new y. So our old y is 0.32. And we're going to add to that our slope times our step. So our slope is negative 0.49. And our step is 0.2. And after we calculate all of that, we are at a y value of 0.222. So still a negative slope, but getting flatter. Still decreasing y values. So we're down here at 0.22. So we have something that looks like that. So our at 1.0, our approximate value is 0.222. That would be the approximate. That would be the approximate value of the function if we use Euler's method with a step size of 0.2, starting at 0, going to 1. And so when we take a look at this, and stop by if you want, if you're a big fan of graphing calculators, which of course you'll need one for the exam, stop by and I can give you a program that does all of the Euler's method steps automatically for you. So here we started at 0.3, and here we ended at 1, 0.222. And so we can see the Euler's method approximation that the calculator generated for us. And I have this program on my graphing calculator, so I can just port that over to yours real easily. This is the actual function that that we have here. And so if we go back up to this expression for the differential, we have y prime, which is nothing more than our dy dx, equals opposite 6x y squared. And we can separate that and integrate it. And so I'm going to go ahead and do that. I'm going to divide both sides by y squared. So we're going to have dy over y squared equals minus 6x dx. And then we can go ahead and integrate that. And so we're integrating y to the minus 2. And so that is negative 1 y to the minus 1 equals, and then integrating that, we're going to have negative 6 1/2 x squared. And so this looks like minus 1 over y equals minus, simplifying this, 3x squared. Or just simply 1 over y equals 3x squared. And then we have a constant of integration here, and we have initial values. So we have at x is 0, y is 3. We know we want to force the function to go through that point 0, 3. That's what causes our particular solution, is when we force it to go through a point. And the initial conditions told us to force it to go through 0, 3. So if we put 0, 3 in, we get a c of 1/3. And again, this is after taking out the negative sign. So we have 1 over y equals 3x squared plus 1/3. So there's the function, and that's what the graph of this is.